Topic 3. Computer registers. The CPU or processor is a small chip that manages arithmetic, logic, input and output, and the basic instructions coming from the hardware or operating system. Its performance depends on three main factors: clock speed, which is how many instruction cycles it processes, cache size, and the number of cores, which can be single, dual, quad, or octa. The CPU has several main components. First, the arithmetic and logic unit, which carries out arithmetic operations like addition, subtraction, and shifting, as well as logic operations like AND and OR. Second, the control unit, which reads instructions from memory. Third, the registers and buses, which act as high-speed storage for processing. There's also the system clock. And finally, the buses themselves, which use parallel transmission, where each wire carries one single bit of data. Now to the core CPU registers, and this is high-priority material. The program counter holds the address where the next instruction can be found. The current instruction register, sometimes just called the instruction register, holds the current instruction that is being decoded and executed. The memory address register holds the address of the memory location currently being read from or written to. The memory data register holds data that has just been read from memory or data that is about to be written to it. The accumulator temporarily stores data during calculations in the arithmetic and logic unit. And the program status word, also called the status or flag registers, consists of 1-bit cells that represent the states of the CPU. Speaking of flags, there are 6 to memorize. The carry flag is set if there is a carry out from the most significant bit. The parity flag is set based on whether there is an even or odd number of 1 bits in the result. The auxiliary carry flag is set when there is a carry out of the lower nibble. The 0 flag is set if the result is 0. The sign flag is set if the result is negative, and the overflow flag is set if the result of signed arithmetic is incorrect. Registers themselves come in 2 types: visible registers, which the programmer can access, and invisible registers, which are for internal CPU use only. The x86 architecture organizes its registers by size. The 32-bit registers are EAX, EBX, ECX, EDX, ESI, EDI, the stack pointer known as ESP, and the base pointer known as EBP. The 16-bit registers are AX, BX, CX, DX, SI, DI, and BP. The 8-bit registers are AH, AL, BH, BL, CH, CL, DH, and DL. There are also segment registers: CS for code, SS for stack, DS for data, ES for extra, and 2 more called FS and G. Topic 1. Overview of modern computer systems. A computer is a programmable electronic device that can store, retrieve, and process data. It works through something called the information processing cycle. In this cycle, the device accepts input, which is data, then processes that input under a set of instructions known as a program, and finally produces output, which is meaningful information. Alongside this, it also stores and communicates data. For a computer system to function fully, it needs 3 things: hardware, software, and a user. Now, a commonly tested distinction is the difference between data, information, and procedure. Data refers to raw, unprocessed facts, such as a person's name, date of birth, or phone number. Information is that same data, but organized and presented in a meaningful way. A procedure is the set of rules or guidelines that people follow when using software, hardware, and data. Putting this together, a computer system has 5 components: hardware, software, the users or people, the data itself, and the procedures. In terms of generations, the 5th generation of computers is defined by artificial intelligence. It uses ultra-large-scale integration technology, supports parallel processing, and incorporates artificial intelligence and robotics. Looking ahead, the next generation includes quantum computing, nanotechnology, and augmented and virtual reality. Computers also come in different types, ranked by power from highest to lowest. At the very top is the supercomputer, the most powerful type, designed for enormous and complex calculations such as 3-dimensional nuclear simulations and weather forecasting. Next is the mainframe, used for millions of simpler calculations and real-time transactions, and built for 24/7 availability with 0 downtime. Below those sit the minicomputer and the microcomputer, which are the standard tiers of computing. Topic 2. Data representation. The fundamental idea here is the binary concept. Computers recognize only two states, on and off, and these are represented as bits or binary digits. A few core definitions. A bit is a single 0 or 1. A byte is a collection of 8 bits. There's also an important combinations rule. Every time you add one more bit, the number of possible outputs doubles. So a group of n bits can represent 2 to the power of n possible outputs. There are 4 numbering systems to know, each defined by its base and its symbols. Binary is base 2, using only the symbols 0 and 1. Octal is base 8, using 0 through 7. Decimal is base 10, using 0 through 9. And hexadecimal is base 16, using 0 through 9, and then the letters A through F next, how human data gets digitized, meaning how each type becomes binary. Text is handled using coding tables, such as ASCII or Unicode, where each character is converted into a number. Sound is captured by sampling it at an appropriate sampling rate. An image is stored as a description of its data points, along with how color is represented at each point. And video is represented as a series of consecutive frames combined with compression techniques. The key takeaway is that all information inside a digital computer is ultimately stored as binary data. Topic 4. Architecture Principles. The von Neumann architecture has been the fundamental architecture for modern computers since 1951. It follows 5 guidelines, and these are likely to come up as a descriptive question. The first guideline is the stored program concept, meaning memory holds both the program instructions and the data together. The second is linear addressing, where memory has a single sequential numeric address for every location. The third is the independence of data and address, meaning memory is addressed purely by its location number, regardless of what data sits inside. The fourth is sequential processing, where instructions are processed in order, and the program counter decides which instruction is current. The fifth is functional organization, meaning the CPU is composed of the control unit, the arithmetic and logic unit, and the registers. In contrast, the Harvard architecture uses separate memory locations for data and for instructions. The comparison between von Neumann and Harvard is the most likely exam question for this topic, so listen closely. On buses, von Neumann uses a single bus, while Harvard uses separate buses. On concurrency, von Neumann fetches sequentially, while Harvard can fetch instructions and data simultaneously. On instruction length, von Neumann allows variable length, while Harvard is typically fixed. And on usage, von Neumann is used in ARM and x86 systems, while Harvard is common in digital signal processors and microcontrollers. Topic 5. The Little Man Computer. The Little Man Computer is a model or simulator, created in 1965, that illustrates how a CPU operates on operands using the von Neumann architecture. It has several components, and each one maps onto a real CPU part. The mailboxes act as the RAM, and there are 100 of them, numbered 00 through 99, with each mailbox holding a 3-digit decimal number up to 999. The calculator acts as the accumulator, providing temporary storage for results, and it performs addition and subtraction using 2's complement. The hand counter acts as the program counter, a 2-digit counter holding the address of the next instruction. The little man himself is the control unit, fetching and executing instructions, and the in-basket and out-basket serve as input through a keypad and output through a display. The Little Man computer follows a process cycle of 7 steps, which is really the fetch, decode, execute cycle in a simpler form. Step 1, check the program counter for the RAM address. Step 2, fetch the instruction from that address. Step 3, increment the program counter. Step 4, decode the instruction. Step 5, fetch data if necessary. Step 6, execute the instruction. And Step 7, repeat the cycle or halt. The instruction set uses numeric opcodes. Opcode 1 is ADD, which adds a mailbox value to the accumulator. Opcode 2 is sub, which subtracts a mailbox value from the accumulator. Opcode 3 is store, which copies the accumulator value into a mailbox. Opcode 5 is load, which copies a mailbox value into the accumulator. Opcode 6 is branch unconditional, which jumps to a new address no matter what. Opcode 7 is branch on 0, which jumps only if the accumulator is 0. Opcode 8 is branch on positive, which jumps if the accumulator is 0 or higher. The code 901 means input, taking a value from the in-basket into the accumulator. The code 902 means output, moving a value from the accumulator to the out basket. And the code 000 means halt, which stops the program. Before we finish, 3 things worth flagging specifically for your exam. First, your slides call it the current instruction register, or CIR, rather than just the instruction register, but they are the same component, so mention both names to be safe. Second, the overflow flag is labeled with the letter V in your slides, but with the letter O in the mock exam. These are the same flag, so use whichever letter the question uses. And third, the little man computer instructions have 2 forms, a numeric form and a mnemonic form. Since the mock exam lists the mnemonics, such as INP, OUT, LDA, SDA, SUB, BRP, BRA, and HLT, write your programs using mnemonics. But be ready to recognize the numbers in case a question gives you raw machine code to trace.